hydrogen atom absorb a photon with the shortest wavelength. So again, this comes back to our picture of an atom and what does it mean for the shortest wavelength. So shortest wavelength in terms of energy, well, we have two equations. We have energy equals Planck's constant times frequency, and we have speed of light equals wavelength times frequency. If we put these together, we get that the energy is inversely proportional to wavelength. So if we're looking for the shortest wavelength, we're looking for the largest energy. Any questions about that part of this? I know I still have to solve the problem. Okay. Now let's talk about how to find that just using these numbers. And one way to do this is to plug all of these numbers into the equation that starts E equals minus 2.18 times 10 to the minus 18 joules. But there's another way to do it. And so I guess next let's tackle the absorb part. So that's our first part. We're looking for the highest energy. Now absorb a photon means that the atom absorbs energy. I guess that should be a colon there. Atom absorbs energy. And when an atom absorbs energy, so there are other ways to do it, but typically when it absorbs a photon, it absorbs energy and moves an electron farther from the nucleus. And moves an electron farther from the nucleus. And so there's two options that are not even absorptions. In our picture of an atom, remember that it goes center, n equals 1, 2, 3, etc. So as an electron moves from 3 to 2, it gets closer to the nucleus, so that's not an option. As it goes from 7 to 6, it's getting closer to the nucleus, so those are not options. And I'll just write closer to the nucleus there. Now, does anybody have a guess as to which of these other two it might be? It's okay if you don't, but...
1 to 2.
So 1 to 2?
Yes.
So now let's go ahead and tackle that equation and see. So the equation that talks about the energy of movements of an electron between n levels is the one we've been working with before. And what it says is that the energy compared to the n values is actually equal, is proportional to 1 over n squared. That's where these squareds in the denominator come in. And so if we move from, well, you can plug numbers directly in. but maybe we should do that. Let's do that because I think I'm a big fan of numbers. So if we do 1 over, let's see, this is going to be my final and this is going to be my initial. So 1 over 2 squared minus 1 over 1 squared versus 1 over 6 squared minus 1 over 5 squared. If I calculate this, so we just did this on a previous problem. This is going to be yes, 1/4 minus 1. This is 0.75. This, I'm going to have to do some higher math here on my calculator. So 36 1 over minus 25 1 over. I get 0.04. So these two terms are the difference in the n values, 1 over n values squared, and they are proportional to energy. So if this is a larger number, it will be a larger energy, and this will be a smaller energy. So Daryl, you were right on. Let me keep that up there just for another second. So we're looking for the larger energy because we're looking for the shorter wavelength, and the larger energy jump would be from n equals 1 to n equals 2. Nice work. Let me zoom out a little bit so you can get the whole picture there for a second. And this is a take-home message, is that as you go from n equals 1 to n equals 2, there's a relatively big jump in energy, and then from 2 to 3 is a smaller jump, and 3 to 4 is a smaller jump, and 4 to 5 is a smaller jump, meaning that the energy levels get closer together energy-wise as you go away from the nucleus.